All right, greetings everyone. It's May 5th, 26. We're in the first discussion on chapter 2. We will be having 2 weeks on this chapter and continue at that pace for now. Uh, we'll begin with any section or quote or figure or question somebody wants to go to. Otherwise, I will provide some quick updates now on the coda. So there's the questions table where you can add questions and review other answers. There are the figures, which we're doing our best, Fraser and Andrew and I, to make sure that all the figures are added for the chapter's upcoming discussion. And also, Andrew has prepared some slides that we'll be building out during the time. Then on the equations page, also through heroic efforts, Andrew and Fraser have added in the LaTeX for the equations, and you can see some cool stuff with the Coda AI. So like plain language explanations of the math based upon the LaTeX underlying the equations. So as we go through different equations, we'll look at this kind of stuff too. So we will jump into chapter 2. Is there an entry point that anybody wants to just begin with, or a quote or a section that they want to start with? Otherwise, let's talk about the outline overall. All right. Well, let's talk about the outline overall and what chapter 2 is doing in the book. Um, Building on the kind of brain in a box thought experiment from chapter, and also just note, Fraser has added some in progress learning materials and kind of ways to run through this. But we'll look at the figure 2.1. Building on the brain in a box thought experiment of chapter 1. We're thinking of this situation where we get sensory observations, we get data incoming, and we're using it to make some kind of inference about external states. And what this book is going to do over the coming few chapters is in a very like micro step by micro step, start with a single state and single observation. So that could be like there's a temperature in the room and we're going to get a thermometer measurements. And that setting of a single state, single observation is kind of like the minimal, crucible, archetypal, observational cognitive situation. And that is going to be used in 2.1 and 2.2 to talk about a few knobs or degrees of freedom within that situation of just single state, single observation. For example, using that as an opportunity to talk about how the generative model and the generative process make the kind of integrated modeling framework, which also introduces the notation and some of the style that Namjoshi is going to use throughout the textbook. Then, in terms of modeling degrees of freedom, like different variants and cousins of models, 2.2 talks about linear or nonlinear generating functions. So essentially, whether a linear regression is being used to generate the relationship between hidden states or latent states and observations, or whether there's some nonlinear generating function, which could be like a quadratic or a square root type. Then, also in 2.2, there will, there's discussion of deterministic and stochastic generative models. So one could imagine that a deterministic generative model is just going to be like a rule-based system, kind of going if then, whereas a stochastic or probabilistic generative model is going to open the doorway to statistics, essentially. That's all in 2.1 and 2.2. 2.3 is going to extend that single observation into a multiple sampling situation. And as we were sort of discussing a little bit right before we started, what's really interesting and exciting is how these algorithms can work in a real time or online or streaming setting, which is to say, like observation by observation, making updates at every single observational cycle rather than, for example, doing batch-based training. And there's a lot of algorithms that work with both or just with batch-based. And what's cool to think about is going into that observation by observation setting, because if you think about how you want an adaptive robot or a model of a biological system to be, it's not like the entity or the agent's going to get 10 observations, then process the last 10. 2.4 goes into some visualizations of the generative model, again, to help us get a handle on what's happening in 2.1, 2.2, 2.3. Then in 2.5, there are some more analytic discussions and probabilistic or gradient descent oriented discussions around ways to fit the model and essentially where you update and how you choose to update. And for now, it's just being introduced structurally, and then we could talk about like what are their computational complexity or resource requirements later on or situationally. So, any general thoughts or questions or like a quote or a section of chapter two that people want to go to? Fraser, and then anyone else.
Just really quickly, I wanted to mention, I did put this in the chat, that chapter two is maybe somewhat mercifully, it doesn't really introduce a lot of new concepts. It's more about, look, we know the lay of the land from chapter one. We've had a lot of stuff introduced. Now let's try and implement that. So it's very much about implementation, this chapter. Although there is a lot of new detail, there's not really a lot of new overarching concepts here. So.
Anyone else? Just well, yeah, Andrew, and then anyone else.
Sure, yeah, just my impression of this chapter overall. I mean, there's not much that's new with reference to what Fraser said as far as like, we have a generative process, and we have a generative model, which align with the notions of having an environment and having an agent. But then from there, of course, for those who aren't familiar with, say statistics or what is a linear, deterministic function or something like that. Of course, from that perspective, we're given a lot of material all at one time. But so one thing that this chapter does is that it kind of works. It tries to use simpler models, such as just deterministic linear functions. Y equals beta 0 plus beta 1 x is a very standard sort of you could do linear regression with that. You could find at any point you could find a slope or something like that, and the intercept, and it just follows that kind of form. But then from there, more importantly, for longevity throughout the rest of the textbook, is that we're going to start seeing once we do have things like noisy processes, and we start looking at things like including priors, so that we can kind of stabilize inference, so to speak, and actually incorporate uncertainty into the computations, we suddenly start seeing the value of doing something like using a Bayesian framework. And then from there, even starting with like looking at entire analytic one-step solutions to like maximum likelihood estimation and maximum a posteriori estimation or inference, instead using gradient descent. And that gives us our first kind of taste of variational methods. So all these things, Bayesian frameworks, variational inference, questions of belief and uncertainty will be, kind of a core primary theme, not just of this textbook, but just active inference and in general. So I just wanted to say all that.
Yes. Okay. Going through the sections, then to the questions that are in the table and in the chat. So 2.1 introduces the modeling framework, and there's the four steps there. Define the experimental setting, define the generative process, define the generative model, and then run and iterate on the simulation. So that should kind of remind you of chapter 6 from the 2022 textbook in terms of those first three stages, part of the recipe for defining essentially a cognitive model. And then here is including in step 4 the runtime, which is going from the fast timescale of inference or perception into the action setting, into the learning or the slower updating. Yes. And in errata, we have that errata is just any little typos or things like that, like figure 2.2, there's no red line. But it's the gray line. Um the red line is there. It's just small. Okay.
Yeah, I think in the
Yeah.
printed book it's not there, but it doesn't really
Yeah.
matter.
Yeah.
Yeah.
2.1.1 is about defining the experiment in terms of a state space. This is really the mapping process itself of abstracting situational features into noted state spaces and then implementing them. Like, what shape is the variable going to be on the computer? So that's where it gets like very clear and practical and disambiguates a lot. And the state space is going to be consider like the state space are all the variables that are going to be stored in the computer for the simulation's unfolding. Anything you have saved time step to time step is in the state space. Anything that's not is not part of your model. Within those variables, some of them, for a given perspective, like the agent's perspective, are going to be observed or unobserved. So even just the case of temperature in the room, you can think about there's the actual temperature in the room, which is part of the generative process. Then there's the observation of the thermometer reading. And then there's the agent's belief about temperature, which is part of the generative model as well. So even just in that sort of three state setting, and then the fourth node in the particular partition is like the action. But for now, just focusing on the perception. 2.12 goes into the generative process. So let's look at equation 2.1. So triangle over the equation is defined as, means defined as. So, and we can add, as we had many great times doing in the previous textbook, like handwritten natural language readings using the active inference ontology, or check out the AI written and curate them if you see um, improvements to make. So if you want to see like a natural language representation, but big picture, the generative process is defining how observations why are generated, including sort of key causal underlying variables and a noise term. And that's going to be a very common way to just model stuff that essentially makes it amenable to doing statistics. It's like the thermometer reading has some signal corresponding to some actual relation between the thermometer reading and temperature, and then there's a noise term, which is what can get fit to the variance component of the um, parametric distribution. We see that similarly in in this in 2.2. Like this is basically like y equals mx plus b. It's just like linear equation. There's some intercept. This is the b. Then there's mx, which is like the coefficient, which is the number before the x. And I'll bring up the figure just so we can connect this to the linear regression. But the linear regression has an intercept, which corresponds to when x is 0. Then this term is going to be 0, and you're just left with the intercept and a noise term. And then as x becomes non-zero, you step away from the 0 line, and the overall trend line or the signal is going to change. And distributional fitting, whether through the one-step analytic or later the variational methods, is basically like you're playing with an Etch-a-Sketch And you can move this Gaussian distribution up or down. You can shift it and you can make it wider or you can make it tighter. And everything in this chapter is going to be first about in the single observation setting and then in the multi-observation setting. How should you update your mean centered belief and your variance estimator on this Gaussian as you get observations coming in? Fraser, then anyone else?
Yeah, just real quick for anyone who's like uncertain or has no idea why we're doing this linear equation where beta 0 plus beta 1 times x. This is a very, he says in the text, we're going to assume that our observations are generated in a particular way from the underlying states. So we saw in chapter 1, we've got a state space, we've got dynamics on that space, and we have observations arising from it. The model that we're assuming is that the observations are given as a linear combination of the underlying states. So that literally means the state multiplied by some number beta 1 plus some other number beta 0. This is an assumption. We could very well be wrong, but this is the modeling assumption that we're bringing to bear on the situation initially, precisely because it's a very, very simple assumption. So that's where it comes from, for those who are unsure.
I see. I also wanted to quickly address question asked in the chat. So theta, the question was theta is a parameter in that equation. Can you explain what that is in your thermometer example? So what we could say first is that so based on this figure here, we see all of the dots. Those are the actual outcomes. Those are the observations that the agent receives. But actually, so it's the trend line itself that itself is based on this kind of model. It's like, well, this is kind of what the values, the outcomes we expect sort of should be. And then the reason why all of those dots are not perfectly on that line is due to noise being involved in the process. And then as far as a parameter and how that goes, just as Fraser mentioned, we have the beta 0 as the intercept, just kind of like kind of your starting point, and then beta 1 being your m, your slope. Or excuse me, no, sorry, that's that is your slope. Then the slope and the intercept become parameters for the model. They say, oh, not only is x related to y, but it's related to y in this particular way, and that's what leads to that slant in the line and so on. So with respect to the thermometer example, I'm not sure how we want to say that, but it would be some kind of parameter, some kind of characteristic or otherwise of the generating process that produces those observations for the thermometer. There would be something about the environment that has some kind of particular shape to it, if you like, and that shaping is shaped by the parameters.
Yeah, great. Like the observation thermometer could be the millimeters of mercury. Because when it's digital, sometimes it feels like it's already in the format that you want. But especially when you think about the physicality of measuring, you're measuring something that's often like in a different domain than the underlying reference. Okay, so that was 2.2. In 2.3, there's the introduction of a sort of large bracketed way to define the generative process. And so we're going to see a ton of sometimes quite different looking, sometimes quite similar looking um, enumerations of state spaces. So here we have Y, the observation generation plus noise. So signal and noise generating an observation. Here, that generative um, process is being clarified here in a way that may seem almost a little bit like redundant, but it's going to give us another articulation. So if you were designing like a software package or something, this is really important. It's going to give us a little bit of an articulation to say we're talking when we say x star and theta like parameters of the generating function. Here we're saying that those are going to be a linear regression, intercept, and slope. But all we're going to have to do to make this into a quadratic is beta 2 x squared. Or that could be some other kind of function. And all you have to do is slot out that part rather than rewrite the first line. Gaussian noise, this is just defining, so just like the second line was defining this first term in better detail, here omega on y is being defined as a parameterized distribution that's n, meaning normal or Gaussian distribution, with a mu mean at 0 and a sigma squared variance, standard deviation. So basically just commonly n and then the mean and the variance of the distribution. And then also theta is being described as the set of parameters for the generating function. So it's just like here, it's kind of repetitively describing essentially the signal and noise components of the generating function. That is going to be extended. This is a good place, though, to get familiar with what these variables are going to mean and how they're going to come into play. Um, there is another way to describe this. So in 2.3, right above, it says we elaborate on the structural form of the generative process. Um, on the next page, for on page 24 in 2.4, this is the probabilistic form of the generative process. So this has a lot of similarities, but it's going to be in a form that is more amenable to essentially receiving it and processing it in a statistics framework, like having the sigma squared be a learnable parameter. Okay, so that was a generative process, generating function, essentially describing the from the environment inbound, the process of signal conveyance and noise generation, like from the room's temperature to the thermometer's reading, focusing just on that first inbound edge. Fraser?
Yeah, I just wanted to quickly note for those who are maybe confused or unsure about what the distinction is between the structural form of the generative model and the probabilistic structural form. They are exactly the same thing. It's just two different ways of expressing the same idea. The latter representation, where we're talking about the probabilistic form, this is just more akin to what we'll see throughout the book later on. So if you're thinking, oh, I really need to get this distinction in my mind, perfectly down pat right now, you don't worry about that. I just wanted to make that clear. They're not two radically different pictures. They're kind of two ways of talking about the same thing. So
Yeah, that's definitely going to come up again. Section 213 goes into the generative model. Okay, so now we're going to be focusing on, from the agent's perspective, what is going to be the belief updating for its model of how the temperature and the thermometer reading are related. And in this initial chapter and situation, they're going to be essentially structurally declared to be equivalent. And one of the advantages of having this kind of partitioned or articulated framework for cognitive agents is they don't have to be the same family of distribution on either side of the observation. There can be a given type of, it can be a exponential generating those observations, and those can get interpreted or something into another family. There's also later elaboration to have the agent also choose like which distribution it should be working with. But in this initial situation, we're just going to look at the generative model that's going to have a already structurally aligned family. Okay, so equation 2.6 is a rewriting of Bayesian joint distributional modeling. Like the probability of hot given a reading of 40 is the probability of 40 given it being hot multiplied by how likely a priori it is to be hot. So this is just like a decomposition of a joint distribution. And a joint distribution is just when there's a comma and we're talking about a distribution over more than one variable. When it's with a comma and it's like it could be two or it could be three variables considered jointly, that's a joint distribution. Vertical line means given or contingent. So contingent means given, a given thing. So it's like, what's the probability of it being hot given that it's sunny outside? So that's a restricted subset of the overall how likely is it to be hot or how likely is it to be sunny. Okay. Now, in the previous section, we were look at no, comma means and. This is the distribution of x and y considered jointly, like a kind of like a blanket draped over a surface, two-dimensionally. Yeah. So in the previous section, the fancy E was the environment for the generative process. Now, in 2.7, we get into fancy M, which is model for a generative model. And here we see a lot of different definitions and arrangements, but it's like the belief about the mean and the variance of the observation given the latent state is normally distributed with regards to that generative with those parameters about the belief about the mean and the variance. So this is how do you go from how likely is a given observation given the latent state? Second line is about general beliefs about how likely a given state is to be in that setting. Here, this is the generative function also which has this linear form for x and theta. Yes, Appendix C2 for basic probability theory, and definitely a good thing to brush up on. And the SPM textbook and documentation, statistical parametric modeling, not to divert, but that book holds up in a triple helix, parametric statistics, non-parametric statistics, and Bayesian statistics. And those are like three big domains of tools at your belt, especially when you're doing the application. And it helps to understand some similarities and differences and like how you can still lock on to a measure of central tendency with a parameterized distribution of central tendency or a bootstrap or some non-parametric method or a Bayesian update. So it's just in practice, they might be differently used. Theta is usually used to mean like all of the parameters, which are here the regression parameters that the agent is trying to figure out. Again, in this situation, it's a linear generating process with a intercept, slope, and noise, and the agent is going to be trying to fit intercept, slope, and noise. Okay, then we get to 2.1.4, inferring hidden states. Equation 2.8 is a rewriting of uh, Bayes' theorem. How you solve Bayes' theorem is going to be one of the big topics. There's a form that can be like the plug and chug form, which is the exact Bayes, which is like when you happen to know these different values, you can just calculate it directly. However, in many situations, it may be intractable, or you may not have direct access, and or you may only be interested in the relative adequacy of different accounts rather than their absolute adequacy. And so in that situation, there are some heuristics that can be applied. And that is especially what's going to come up in the variational inference section. Um, and it is also discussed a little bit in 2.9, which is where y hat, the hat is going to refer to a clamped variable. So that's going to mean like we're talking about one specific spike-like instantiation of a given variable. So not just generally how do those variables relate to each other, but it's like this is like what's the probability of X given that Y in general equals this specific Y? What's the probability of the heat being, of it being hot given that the thermometer said 39? So that kind of operationalizes the generic Bayesian theorem into something that's getting us closer to um, calculated, being able to calculate. Okay. Then we get to 2.4. Oh, so here's the likelihood example, but let's look at 2.4. Okay. So here is summarizing the previous sections. We have fancy E, the environment, aka the generative process. And we have fancy M, the agent, aka generative model. Right now, we're still looking at an agent that is going to get an observation and make some belief updating. They're not going to take an action yet. So the agent side is relatively simple, basically the minimal form, where there's some observation that's just empirical, it's factual, it's 711 millimeters of mercury. Then there's the belief about the temperature, which is mediated by an observation model or recognition model or a matrix, or essentially just a mapping between how do you go from an observation to a belief about latent state. Mark?
Yeah, I just want to try to articulate this P of Y. It's this intractability of the model evidence. It's often it's evaded me, and I've thought long and hard about it. I'm wondering, in a sense, if we're looking at just something that is almost like a model decision. So, in other words, given the high dimensionality and all of that, it's hard to account for every possible reason why you might have an observation. But maybe the simpler way for me to wrap my head around it is that most of those are irrelevant to what the kinds of questions I'm asking. Is that a fair way to look at it? So it's not that it's just computationally intractable, which I don't quite fully grasp that, but it's like I'm not going to concern myself with these other causes, given that my experience would suggest this. My model is, in a sense, going to clamp that Y, or at least restrict it to, X possible dimensions. I shouldn't have said X. A set number of potential explanations. Am I circling that?
Andrew, give a thought. Sure.
Yeah, sure. I was gonna respond directly to that. There are many different ways we could say this, and like kind of as far as like the variational methods and marginalization and things like that go. The simplest way of saying it is like, whenever I'm going to go to the store and I'm here in Chicago, like despite the fact that my model technically has all kinds of information that have nothing to do with the store or being in Chicago, like I have some awareness of like what the mapping terrain is in California, but that doesn't necessarily mean I need that. So this kind of loose, slightly crude example I'm giving is just to make the point that like by being able to sort of marginalize or kind of isolate out the relationships between particular factors, you can kind of use the information that's more so like kind of at hand. And then that allows for overcoming, because in this chapter we look at very simple problems where we actually can do something like we don't have to marginalize necessarily. We can just take the entire like one step analytic solution and find like, oh yeah, this is exactly the posterior. We didn't have to do any variational stuff at all. But this is an extremely simple example that we're seeing in this chapter. We're just seeing the relationship between an observation with light intensity and a state is like how much food is there. And of course, like most of the problems that people face and even animals and life forms face are much more complex than just the relationship between one specific number, that being light intensity, and another number, that being food source. Although, of course, there are many problems we solve on paper all the time that are that simple, but usually things are much more complex. I hope that was useful in some way. I know it's a big idea with a lot of thoughts behind it, and the textbook will definitely go further into this kind of variational stuff as we go.
Thank you. Terry?
On that topic, this has been a constant. I mean, I've satisfied myself that I can understand that it's intractable because, like, the chances of getting observation Y, if it is an alien spacecraft over the White House, for every possible state of a universe, it's going to take you a billion years to think of all those. And if you're a living agent, you can't actually do it in the time allotted. So I've kind of got that. But I remember Friston trying to explain this. And again, just like Andrew said, he talks about marginalizing. And I'm not a mathematician. And it seems to be that that you have that to get Y, you have to remove X from a probability of X and Y, do you? To get to so you kind of know the probability of X and Y, but you have to remove by some magic thing called marginalization. And my question is, Andrew, what does marginalize? He says that she worked it out in the margins of the book, and but what is the process of marginalizing to get rid of the X?
Yeah, yeah, so I'll quickly say, and I tried to summarize this in a kind of oddly typed comment in the chat, but at one point I put, um, so the probability of X does not equal the probability of Y, does not equal the probability of X conditioned on Y, does not equal the probability of X comma Y. So all these are different terms. So if we only had probability of X, then that means we have our prior beliefs about what X should be. We have some beliefs about what states are. That means nothing about observations. That means that one, we don't know anything about observations, nor how they relate to X, how they relate to states. And then conversely, if we have probability of Y, similarly, we know that's if we only look at that, then we're saying nothing about states because the X is not in there. It's just probability of Y. It's only once we start to have some kind of likelihood mapping, like probability of Y conditioned on X, conditioned on being that single vertical bar, that we actually have a way of relating X and Y, right? And then once we have that, or you could even still treat them separately, but whenever you combine everything together, you could also look at the joint distribution, which is the probability of X and Y kind of co-occurring. So whenever we kind of play around with these and we say like, well, what if we have this massive joint distribution? We want to know about all the relationships between X and Y. It's P, the probability of X comma Y. So it's everything all together. One thing that we can kind of do is that we can start to marginalize out certain terms, such as probability of X by itself, where we do certain kinds of things that, apologies, it's kind of skipping ahead, but we'll do things like summing all overall values of Y in order to kind of come up with like a good estimation of like what should probability of X be, things like that. So it's kind of in the plainest, most abstract, unfortunately, terms possible. It's like we're kind of just changing these terms around to try and get at just one component of them out of this massive XY space. We're trying to only pull out X. We're trying to only pull out Y. And then we can say, oh, we pull out the X, so now that's our marginal distribution of X that we kind of abstracted out. And that becomes, yeah, it becomes really important because otherwise, usually that probability of X comma Y space is essentially intractable if we try to compute anything with it. It's massive. We have to update, every small value. And then, of course, once we expand beyond the example in chapter 2, where we're just looking at a single X variable and a single Y variable, to suddenly we have hundreds of X variables and hundreds of kinds of observations that an agent can receive all at once through sight, through sound, through all the rest. then suddenly we need something like like marginalization and variational
Yeah.
methods.
Would a
It
way,
might
There's
be
just
to show equation or figure 2.24. I don't know if we want to move on or not, but that's a very nice visual depiction of these ideas.
figure
could
what?
I just
2.4?
ask Andrew,
2.24.
would, could I ask Andrew a question, a feedback, or a follow-up?
Please, yeah.
Yeah,
If
I'll be more concise
would
in
a
my
way
answer.
for no would a way for a stupid non-mathematician be that marginalization is clever mathematicians using different mathematical complicated ideas to get rid of the X value to come up with the probability of Y. But the process of marginalization isn't a process. It's clever maths like physicists on a blackboard doing loads of things to get rid of a value they don't want. And you'll apply different processes depending on the way the data is presented. It's not one operation. Without is that a? I know that that's probably not what it is, but is that an acceptable way that a non-mathematician brain could imagine the process?
It
I would
is. It is
I would say
basically a
that's fair, but I would be careful about the nuance behind the word clever, but I see exactly what you mean. So we want to make sure that when we say clever, we don't mean like kind of deceptive or skewing things. Instead, we want to, but it is something
No,
you
I
would
mean
work out on a
smart. I
blackboard.
mean smart.
Because what you're
Smart.
doing is that what you can do is kind of exploit particular characteristics of different existing mathematical like elements or objects or otherwise. For example, things that we'll see commonly is replacing particular variables with a log form because thanks to these really nice natural properties of logarithms, it simplifies things immensely. It can take an entire like big like product like multiplication based problem and turn it into a simple sum problem, which we see later in this chapter on like gradient descent and things like that. So it is using certain kinds of, I guess, clever techniques. I think is fair. I mean, it took time to discover those, but yeah, but they always come back to like kind of these natural
Yeah.
properties that we find in the
But,
math. It's nothing that's forced per
yeah.
se.
Like we'll return to this many times, but the marginal is literally the margins of a spreadsheet. What's the probability it's hot given it's low? You can just, it's basically a flattening on a spreadsheet. That's the origins of it, and it gets extended into these more high dimensional and probabilistic settings. But just in our last bit of this first session, let's just look ahead to what the coming sections are going to take us through, and then there will be Fraser's diligent session later in the week, and we'll return to chapter two again next week. By which time, like people can write more specific questions. But just looking ahead to the next um, pieces of this chapter, so we kind of have scanned where we're going to go in this chapter. In example 2.1 on page 30, we see figure 2.5, which is introducing us to a Bayesian network or a Bayes graph, focused on that critical inference around given a clamped variable, which is shown in gray, y observation, and actual observation, and beliefs about the process leading to those observations, how are you going to update your belief about the hidden state? So that's the crux of this chapter and essentially what is going to come. So that's example 2.1 in this linear deterministic generative model setting. And that's explored more in the food particle example, which maybe we can use interchangeably or instead of the temperatures. Uh, Page 32, example 2.2 goes into linear probabilistic generative model. Example 2.3 on page 33 is going to go into how much should you relatively weight the prior confidence, essentially. Whether the prior should be very precise, like a very assured belief about how food shapes are distributed, it's 4 plus or minus zero point 0.1, or is it a much more dispersed distribution a priori about beliefs about food. And you can even just qualitatively imagine, like, if you have very strong beliefs in what you believed before, the observation is going to have less impact. If you have more flexible or flatter beliefs about before, the observation is going to have more impact. So that comes up many times. Page 34, example 2.4, goes into a nonlinear deterministic generative model. So that's equation 215. So now we see that there's this psi variable, which is a quadratic transformation of x. So it still plugs into the same top line with the generative outcomes being produced by some g sub fancy e, and then it's just, instead of being intercept plus a linear coefficient on x, now we have a linear coefficient on x squared. But that is kind of exposing us to this broader polynomial family of generating functions. So it could just be like the linear, which is actually a polynomial of just highest degree being linear, but then it's like to the third power, fourth power, fifth power, things like that. Example 2.5 is going to continue our exhaustive sweep because it's a nonlinear probabilistic generative model. Example 2.6 in equations 218 and 219 is going to look at the situation where the generating function is linear, yet the generative process has this nonlinear transformation. So that's kind of giving a demonstration of where there in fact between the temperature and the thermometer reading there is a quadratic relationship, but the agent is modeling it as if it's a linear regression. So that would be like applying a linear regression analysis to a data set that actually had a quadratic curve. And again, there's a higher order of model selection where you could explore or feature learning in more of a machine learning setting, like which transform, linear or quadratic, you should use. But that's just showing us, like, yeah, in principle. And that's what people suggest can contribute to the generality and the flexibility of active inference agents is kind of like um, by knowing what shape the beliefs about observations are from the inside out, a wide variety of external situations can be handled without needing to know what every external situation is. Like, because we have beliefs about color and light intensity visually, we have potentially open-ended visual perception. Section 2.3 extends into multiple samples. So that just goes from the single one-shot update situation, which is, again, like, it is the crux of the game. That's like the pitch in baseball. But now we're looking at multiple observations coming in sequentially. That's a pretty short section. Section 2.4 asks, so far we have spent extensive time discussing the prior and likelihood, but have neglected to discuss the generative model itself or examine its structure. What does the generative model really encode internally, and how is it able to capture all the information that the agent knows about the environment? So you can think about the generative model plus the process, so E and M, to be like everything the modeler knows about the situation. And then the generative model considered alone is everything that the agent knows about the situation from its restricted awareness. Section 2.5 is going to onboard into hidden state estimation without Bayes' theorem. and walks through that in a more classical setting. That is going to introduce two ways to update beliefs about latent spaces, hidden states, given an observation, which is the MLE and the MAP, which is two different strategies that we're going to go into more detail in about how you can use different approaches to make that inference about a latent space. 2.5.2 goes into an iterative solution, which is going to start to tease one of the most fascinating and advantageous aspects of this framework, which is turning a tractable or intractable one-shot calculation problem into an iterative gradient-based optimization. And 2.6 is the summary and the conclusions. So if we pull back to the figures, we start with like this minimal crucible template. Like a pizza is the dough, the sauce, and the cheese. Just one of them. And then each of those things, we see that there's actually a few different options for them. And those are what the experiments and the different examples in the chapter are getting into, is like saying like, well, you could have configuration 111, you could have configuration 112, you could have 121, 221, and starts to walk through some of those articulations. It's kind of like learning these dance moves. Like you could lift up your left leg, but not your right leg, or you could do the left leg and the right arm. And then by seeing like, okay, it could be that way in this minimal case. And you can see which things are kind of welded together and among models, what opportunities for difference are there. And then for a given situation, what is the actual inference? And then that becomes especially important if we want to do not just a single observation once, but we want to do a batch of sequential observations or eventually like a real time or streaming play by play, which is what is approximating the kind of sensory flow and the unfolding of action in the world. So in last minutes, just any section or question or thought that we could note down, or what do people want to explore more in the section later in the week or next week? Yep, Fraser.
I'll just note, I mean, the main idea of this chapter is we're trying to do hidden state estimation. We're trying to do perception. So I get some observation, and I need to account for that in terms of inference about what I think the environment is like. That's all this chapter is trying to do. There's then another story about how I select actions to change the environment to be like what I want it to be. But we're not looking at that just yet. We're just passively, if you imagine the agent, right? We're just sort of sitting there and not doing anything. Stuff is happening. We're observing stuff, and we're trying to come up with a hypothesis about what we think is really going on. That's kind of the name of the game for this entire chapter. So it's only point A of that loop that we saw in the initial part of the chapter.
Yeah, and just to pick up on that, Fraser, it's about getting an observation, and based on that observation, trying to infer the hidden cause that caused that observation to be issued by the environment.
So many fun ways to take it, and it's kind of like the characters getting introduced in the beginning of a novel or something. Like action is going to fit into this setting so seamlessly and fascinatingly. And this is a path of learning that Namjoshi has, I'm sure, trialed and tortured many with to find out what steps will walk us to the point where when we say, okay, now what if we were going to treat action as another variable to do inference on? And instead of just doing a totally secondary kind of control theoretic add-on to a signal processing framework, we're actually working in this very general setting where introducing action is going to be something that is not like a no but or a yes but it's going to be already integrated within the same notation and ontology that's helping us understand even these minimal settings. Terry?
Um, so a question, I'm trying to get this straight in my head that um, so far in this chapter, we're kind of saying that for a given observation, there is a state of the world, right? And that there's a kind of linear relationship in this model between the observation and the state of the world. So it's almost like, but we're not really talking about the agent having predicted a potential state of the world before making the observation. We haven't really got to that stage yet. Am I,
We
or have I,
have. That's the
have
prior.
we? Yes, but have we talked about a prior? We've talked about you collect an observation and then you drop a line down to X and then that tells you what X is. We haven't really sort of said, before I make my observation, I am making a prior assumption about the world, and then I'm going to make my observation. We seem to be more talking that there's a single figure that is the value of X for any given Y, rather than, and I know we've spoken to a bit of a, Gaussian around those things, but it feels like the conversation hasn't been about the agents making a prior assumption about the world, does an observation, and then formulate and then updates its model based on the observation. That's the way it's come across to me so far. And I'm thinking,
Yeah.
have I missed something?
Ch check out page 40 and 41 again, where this image comes up, and you'll see that relationship. But absolutely, it hasn't been discussed in like a predictive processing, brain as scientist, anticipatory belief, experiential prediction, like a lot of these kind of deeper senses. But yes, there is still the implicit um, encoding of prior beliefs before the observation comes in. It's just not being discussed in a sort of like enacted psychological sense. Okay, Mark, and then any last comment?
I was just thinking that we were looking at the mapping of causes to states. I mean, that seemed very much uh, like more of a likelihood mapping. Is that right? But the prior is there sort of interacting with that, just like you have here in this chart. But I would say that, am I right in when we spent some time looking at the generate function, that's more of the likelihood term. Is that just to kind of build on what Terry was asking? Is that a fair assumption? Just to make sure I'm not conflating these terms.
Andrew, you give the last comment, then one.
Oh, wait, well, yeah, it was just to answer that. So the prior, think of that as P of X, like probably, P parentheses X, on parentheses. So that's P of X. Likelihood here is actually P of Y conditioned on X. So Y vertical bar X. So they're two distinct things that kind of get used together to generate your posterior. So recall that Bayes' theorem has exactly those terms, right? It has the prior and it has the likelihood. And then we mentioned model evidence, but that's just P of Y, right? So really it's the way that we can kind of use these together to result in that final posterior computation. The posterior being probability of X conditioned on Y, right? So it's just the flip of the likelihood.
Cool.
Yeah.
Also,
And
yes, please write your questions, or if you don't for whatever reason, find the page or have access or anything like that, like email them. We'll put them in the table. Um, Fraser and Andrew and I will try to answer. And truly, it is a unique and priceless opportunity to have these fellows address your written questions about this book. So, as if you were in like a learning setting where you can get your actual specific questions answered. So, thank you all for joining. See you later.